Welcome back to this next video in which we are discussing field extensions. Okay, so what we've now seen is that indeed when you quotient out the ring of polynomials over the field capital F by the principal ideal generated by an irreducible polynomial p of x, you do indeed get a field extension of your initial field capital F which contains a root to the polynomial p of x. Okay, what I want to do in this next video is try to understand this field in more detail, and we've called this field extension K to shorten the notation. What I now want to do is actually try and characterize the elements of K. Okay, we know that it's going to be the additive cosets of the principal ideal generated by p of x, but what I'd like to be able to do is name all of these additive cosets, all of these cosets. I'd like to find some representative of every single one of the cosets that we will name the coset after. I will take that representative, which is some polynomial in the ring of polynomials over the field, and stick a bar over it, and that can be the name of the coset. Okay, so I'd like to characterize the elements in this field so that we can understand the field better, because at the moment we don't know much about it at all. Okay, that's my hope, that we're going to have a decent understanding of this, and the first thing that we need to do is actually understand what are the elements. Can we characterize these cosets? And it turns out that we can. Okay, so I'm going to tell you the fact, okay, and then we'll spend a bit of time understanding why this is true. Okay, so here's the fact that each of these cosets can be characterized by a polynomial, which I will call r of x here, which will have degree strictly less than the degree of the polynomial p of x, which we previously called n. Okay, so the degree of my polynomial r of x will be less than n, strictly less than n. Okay, so this is my claim that all of these cosets here will absolutely always contain a polynomial which I'll call r of x, which has degree strictly less than the degree of the polynomial which we use to generate this principal ideal, which we quotiented out by. Okay, so strictly less than n here. Therefore, those are the polynomials that we're going to use as the representatives for all of these cosets, and we're going to name all of the cosets after those polynomials. What is more, all of the different polynomials in the ring of polynomials over the field that do have degree strictly less than n are all in separate cosets from one another. Okay, so this is looking absolutely beautiful. Not only does every single coset contain a polynomial of degree less than n, but all of the polynomials of degree less than n are in separate cosets. Okay, so in fact we can completely characterize our field extension by these polynomials that are in the ring of polynomials over the original field capital F that are of degree less than n. Okay, and that's what I want to convince you of first here. Okay, right, so I'm going to start off by showing that any coset is always going to contain a polynomial of degree strictly less than n, a polynomial r of x here. Okay, so how am I going to show that? What I'm going to do is I'm going to take some arbitrary polynomial, and I'll call my arbitrary polynomial a of x here, which is from the ring of polynomials over the field capital F. Okay, so a of x is some arbitrary polynomial in the ring of polynomials over the field F. And what I want to show is that this arbitrary polynomial is always going to be in the same coset as a polynomial of degree less than n. Okay, so hopefully you can understand that if I show that, then I would have indeed shown that all the cosets contain a polynomial of degree less than n, because all of the cosets contain polynomials. If I can take an arbitrary polynomial and show that it will exist in the same coset as a polynomial of degree less than n, then I've shown that all of the cosets must have a polynomial of degree less than n in. Okay, so how can I do this? Well, of course, we're going to use the Euclidean algorithm. The ring of polynomials over a field is a Euclidean domain, so we can use the Euclidean division algorithm. Okay, sorry, not the Euclidean algorithm, the Euclidean division algorithm. Okay, so what I can do is I can take my polynomial a of x. Now, there are two cases here. Either a of x itself is actually a polynomial of degree less than n. If a of x is a polynomial of degree less than n, you're done. Okay, absolutely fine. We've proven that that coset does indeed contain a polynomial of degree less than n. If it's not of degree less than n, then what you can always do is perform the division algorithm using the polynomial p of x. Okay, so what I can do is I can write a of x here as some quotient polynomial, which if a of x has degree n, the same as the polynomial p of x, will just be a constant polynomial. Okay, if it's got degree greater than n, then it will be more interesting, times the polynomial p of x plus a remainder polynomial r of x here. And what can you say always about the degree of this remainder polynomial? You can say that the degree of the remainder polynomial is strictly less than n. Okay, so because the ring of polynomials over a field is a Euclidean domain, we can do this. You can always take your polynomial a of x, which we're assuming now has degree greater than or equal to the degree of your polynomial p of x, which is n here, okay, and you can always write it as some quotient polynomial times the polynomial p of x, and then you have to add on this remainder polynomial, but you can always arrange this. You can always pick your quotient polynomial and your remainder polynomial cleverly enough such that the degree of the remainder polynomial is strictly less than n. Okay, so it's always possible to find an expression. It's always possible to find a q of x and an r of x such that this is true. Okay, now why is this interesting? Well, of course, look at this. Q of x times p of x. Okay, that is exactly something that's going to be in the principal ideal generated by p of x. Remember, the principal ideal generated by the polynomial p of x is just the polynomial p of x multiplied by all other polynomials in the ring of polynomials over that field. Okay, so this is certainly going to be an element of the principal ideal generated by p of x. Then all you've got is this remainder polynomial r of x plus an element of the principal ideal generated by p of x, and that's giving you a of x. So what that is telling us is that a of x is going to be in the same additive coset of the principal ideal generated by p of x as r of x, okay? So let me just draw a little picture here. So if this is our ring of polynomials over the field capital F, okay, now add some colour onto here. So this is our initial starting ring of polynomials over the field capital F. Then of course, to construct the field extension, what we've done is we've taken the principal ideal generated by the polynomial p of x here. Okay, and I'll colour this in green here. And we've then quotiented out, we've partitioned up the ring of polynomials over the field capital F into the additive cosets of the principal ideal generated by p of x, like so. Okay, now what are the additive cosets of this? Well, if we have some element, let's say r of x, for instance, r of x, this polynomial r of x here, will be in an additive coset. It will be in one of these cosets. Then how do you find all the other elements that are in the same additive coset as it? You add elements that are in the principal ideal generated by p of x to the polynomial r of x. This is an element in the principal ideal generated by p of x. You've added that onto r of x, so another element that will be in the same additive coset as r of x is going to be this polynomial a of x. So the two are going to be in the same additive coset. So what I have now successfully shown then is that you take an arbitrary polynomial, it will be in the same coset as some polynomial which has degree strictly less than n. Okay, so that now shows that every single one of the additive cosets of this principal ideal generated by p of x in the ring of polynomials over the field f is always going to contain a polynomial of degree strictly less than n. Okay, and just to write this explicitly out, r of x will be something of this form: r0 plus r1 plus all the way up to potentially n minus 1, x to the n minus 1. Now, of course, it doesn't necessarily have to have degree n minus 1. Rn minus 1 here might be 0. What we can say, however, is that all of the coefficients for the powers of x higher than n minus 1, so from x to the power of n upwards, are all equal to 0. Okay, so here's our polynomial of degree less than n. So every single one of these cosets is going to have a polynomial of degree strictly less than n in it. Okay, but that's only half of the story. That now shows that indeed, yes, we could represent all of these cosets by a polynomial of degree less than n. What I now want to do is show that every single polynomial of degree less than n is in a separate coset. Okay, so there is no coset that contains two polynomials of degree less than n. They're all in separate cosets, and therefore they completely characterize the cosets. Every coset is representable by a polynomial of degree less than n, okay, and all of the polynomials of degree less than n represent a coset, so it works both way round. They're in bijective correspondence, basically. Okay, that's a nice way of saying it. There's a bijective correspondence between the polynomials of degree less than n and the cosets that we're going to get, i.e. the elements of our field extension. Okay, so this is all getting rather exciting. So what do we need to prove? We need to prove that no two polynomials of degree less than n can be in the same additive coset. Now, how are we going to do that? Well, we're going to do it by a proof by contradiction. We're going to assume the opposite of what we want to prove. We're going to assume we have two polynomials of degree less than n that are in the same additive coset and arrive at something ridiculous. Realize that something impossible has happened. Okay, right. And so, let's say our polynomial a of x, okay, now it's a different polynomial from here. Now a of x is some polynomial of degree less than n, okay, and b of x is also a polynomial of degree less than n. Okay, so both of these are polynomials, okay, in the ring of polynomials over the field capital F. Okay, and I'm supposing now that the degree of both of them, so the degree of a of x, and indeed also the same statement for the degree of b of x, I'll just write this out quickly, that they're both less than n. So both of these polynomials are degree less than n. And now what I'm going to assume is that they are in the same additive coset and arrive at something silly. Now, what does it mean for them to be in the same additive coset of the principal ideal generated by p of x? Well, it means that I can write a of x as b of x plus some element of the principal ideal generated by p of x, just like this expression here. Okay, so plus some quotient q of x times the polynomial p of x. And I could have used some different notation here. Okay, it's not a quotient in this case, but it's just now being used, just to use the same notation as here, but it's just some arbitrary polynomial in the ring of polynomials f of x. So this is a statement in the ring of polynomials f adjoin x here. Okay, if a of x and b of x are going to end up in the same coset when we quotient out by the principal ideal generated by p of x, then this statement must be true in the ring of polynomials over the field for some q of x here. Okay, right. So, how do we arrive at something silly then? Well, what we can do is we can take b of x here onto the other side. Okay, so I can say, okay, let's add on the additive inverse of b of x, which is the polynomial where all of the coefficients are just the additive inverses in the field capital F. Okay, let's add that onto the other side. So we'll get a of x plus the additive inverse of b of x is equal to some multiple of the polynomial p of x in the ring of polynomials over the field capital F. Now, why is that something impossible? Well, it becomes something impossible when you acknowledge that when you add a of x to the additive inverse of b of x, the resulting polynomial that you get once you've added these two polynomials together, it must have degree less than n. Now, why is that? Well, because this polynomial had degree less than n, you're now adding it to the additive inverse of this polynomial, which also had degree less than n. When we took the additive inverse of this polynomial, all we did is stuck negative signs in front of the non-zero coefficients. We didn't change the degree. Okay, when we add these two polynomials of degree less than n, we just add the coefficients. So again, you don't change the degree. So the degree of this must be less than n. Okay, also note that I'm assuming a of x and b of x are not equal to one another. Okay, so I should have just put that here. We're assuming they are not the same polynomial. Okay, so that means that when we add this polynomial a of x to the additive inverse of b of x, we do not get the zero polynomial. We get some non-zero polynomial here. And I am now saying that I have a non-zero polynomial of degree strictly less than n that is a multiple of my polynomial p of x, which has degree n. Now that's not possible in a ring of polynomials over a field. Because a field is an integral domain, you've got a ring of polynomials over an integral domain. And whenever you've got a ring of polynomials over an integral domain and you multiply two polynomials together in that ring of polynomials, the degree of the product is always greater than or equal to the degree of the two polynomials that you had multiplying together. So it will in particular be greater than or equal to the degree of the polynomial p of x, which is n. So this product is going to have degree greater than or equal to n. The only exception to that rule is when you multiply the polynomial by the zero polynomial. So if p of x was the zero polynomial, then of course you end up with the zero polynomial, which doesn't have a defined degree. We don't bother defining the degree of the zero polynomial. Okay? So that's the only exception, but we've said this isn't the zero polynomial, so we can rule that out. Okay, so here we have an impossibility. We have something that has degree greater than or equal to n, equaling something that has degree strictly less than n. Okay, that's rubbish, basically. That statement is rubbish. So something has gone wrong. So now what we can assume is that our assumption that we could have two polynomials of degree less than n that were in the same additive coset of the principal ideal generated by the polynomial p of x was wrong. Okay, so to summarize all of this then, we have proven this bijective correspondence. Okay, there is a bijective correspondence between the polynomials from the ring of polynomials over the field F of degree less than n and the cosets that we're going to get, and indeed our elements in the field extension K now. Okay, so every single one of these cosets can be represented by a polynomial of degree less than n, strictly less than n. Okay, so what you'll do is you'll go through your start again. If you've got some coset here and you want to decide what it should be called, and we might as well take this one here that I've already got. So you have got some coset and you want to decide what should it be called. You search through it to find the polynomial of degree less than n, and there will only be one. Okay, only one polynomial of degree less than n will be in this coset. You find that polynomial, and that polynomial is going to be the representative for this coset. So what we're going to do is we're going to name the coset this polynomial r of x here, and we'll just put a bar over it, the coset that contains that polynomial. Okay, so we've now characterized the elements then in our ring of polynomial, in our field extension. Okay, they are represented by these polynomials of degree less than n. What I now want to show you is that we can actually find a very nice basis for our field extension over the original field capital F. Okay, so this characterization of the cosets in the field extension now leads us to being able to find a very nice basis for the field extension viewed as a vector space over F. Okay, right, so my next claim then, where should I do this? Shall I go into a new piece of paper? I think I will. Okay, so my next claim is going to be with regards to finding a basis for my field extension K over the field capital F. So I'll just remind you that K is this quotient ring that we have now constructed, where we've taken the ring of polynomials over the field capital F, and we've quotiented out by the polynomial the principal ideal generated by the polynomial p of x. Okay, this is now a field extension of the original field capital F, and we now want to find a basis for it. Okay, so we want to view it now as a vector space over F, and we want to find a basis for it, and this is going to be this is going to allow us to be able to make a comment on the dimension of this field extension over the field capital F. Okay, right, so how are we going to do this then? I'm just going to tell you the basis, and then we're going to prove that it's a basis. It's a very natural basis, you could probably guess it. Okay, so remember, a basis is just a set of vectors from the vector space, which in this case is our field extension K. Okay, so what am I going to pick? Well, first I need a definition. I need to define the terminology I'm going to use, the notation I'm going to use. Okay, so I'm going to use the symbol theta here to represent one of the cosets in here. Okay, and it's going to be the coset that contains the polynomial x. So the polynomial x is a polynomial in the ring of polynomials over the field. It's the polynomial where you've got a 1 in front of x to the power of 1 and zeros in front of all the other powers of x. Okay, it's certainly a polynomial of degree less than n, because remember, when we chose that polynomial p of x, we assumed that it was degree 2 or greater. Okay, so we assumed n was greater than or equal to 2, so that's all fine. Okay, and it will be in a coset on its own with no other polynomial of degree less than n. Okay, so I'm going to represent that coset x bar as theta. okay, to get rid of the barred notation, to start viewing this as a field in its own right now, okay, rather than just as this quotient ring. Okay, so now we're going to have a basis which is going to be 1, the multiplicative identity, which of course will be the coset containing the multiplicative identity from the original field, but we're going to start to try and edge away from the barred notation. Okay, we want to start viewing this structure as a field in its own right. Okay, so I'm going to not put the barred notation there. Okay, we now know what that means. We know that we can think of f as being contained within this field extension. Okay, and we know, you know, that really the elements that correspond to it are those cosets that contain those elements, but of course we're never going to use a different representative of those cosets other than the element of the field that was in that coset, so we might as well just do away with the barred notation. Okay, and we're going to start to try and, as I say, edge away from the barred notation. Okay, that's the way people normally do it. We'll take the multiplicative identity of our field extension here. We'll have theta, okay, and then we'll go up. We'll have theta squared, so theta multiplied with itself in this field extension. Okay, so you'll be doing multiplication in here, okay, and then you'll continue on all the way up to theta to the power of n minus 1. Okay, so whatever n, the degree of the polynomial p of x was, okay, you'll go up to 1 minus that with these powers of theta. Okay, so the first thing to ask is, what are these powers of theta? Which cosets actually are those? Okay, so go back to thinking in terms of cosets, the barred notation. What actually are these cosets? So if I take, for instance, theta to the power of I, so that means this element, theta, of the field multiplied with itself I times. Now, how would you perform multiplication in this field? Well, of course, you take a representative from the coset and you would multiply it with itself I times, okay, and get the answer in the ring of polynomials over the field, and then take the coset that contains that. Now, which representative are we going to use from this coset? Well, of course, we're going to use the representative x. So what we'll end up with is the coset then that contains x to the power of I, the polynomial x to the power of I. Okay, now of course we're assuming I is strictly less than n here, because we don't go past n minus 1, we go up to n minus 1, so we certainly don't get up to n. Okay, so I is less than n here, so of course x to the power of I is a polynomial of degree less than n, so this will be a coset that is distinct from all the other cosets in this field extension that we've got here. Okay, so these are elements of our field extension K, and all of these are distinct elements. Okay, that's the argument here, that we know that this polynomial that is also of degree strictly less than n is going to be in a different coset to all the other monomials of degree strictly less than n. Okay, right, so that's all fine. Now what I want to prove is that this is indeed a basis. So we've got these collection of elements from my field extension K. What I want to prove is that this is a basis for K viewed as a vector space over F. Now what do I need to prove? I need to prove two things. I need to prove that it spans the field extension K, and I also need to prove that they are linearly independent vectors with respect to the field F. Okay, so let's start off with spanning. Okay, so I want to make sure that it spans the entire field extension K. Okay, well, hopefully that should, of course, be obvious. Okay, this isn't too difficult. It's just, we do need to do this to make sure that everyone understands, okay? We do need to go through all of this to get a full understanding of this. But it isn't difficult. If we consider a linear combination of these basis vectors, what we're going to do, of course, is we're going to just multiply these elements by the elements of the field capital F. Okay, now again, I'm steering clear of the barred notation, so I'm now just going to denote the elements of the field capital F without the bars, but of course, when we multiply them with these elements of the field extension K, it will be multiplication of the cosets, but of course we'll just use the representative that is the most obvious, which is the element of the original field. Okay, so I'm steering clear of the barred notation, so we're going to have A0 times 1, okay, now of course 1's the multiplicative identity, so I won't even bother writing that, plus A1 times theta, plus A2 times theta squared, plus all the way up to an minus 1 theta to the n minus 1, where all of these ai's are from the field capital F, okay, which you can now view as a subfield of K. Okay, so of course multiplication here just means multiplication of the coset that contains this, which now we're just going to represent without the bar notation, times theta, this coset that's in the field extension. Okay, so what I want to show then is that I can get any element of my field extension K. I can get any coset within the quotient ring of the ring of polynomials over the field by the principal ideal generated by P of X. Now, why is that going to be true? Well, how am I actually going to perform this multiplication? Well, of course, what I have to do is take representatives from each of these cosets. So I know which representatives I'm using from the cosets that contain the elements of the field. I'm just going to use the elements of the field. Which representatives am I going to use from these powers of theta? Well, of course, I've already agreed this. We're going to always use the polynomial of degree less than n. So we're going to use these monomials here. Okay, we're going to use those representatives to perform these multiplications and these additions, and then we're just going to take the coset that contains the polynomial that we end up with as our answer. Okay, so what polynomial will we end up with? We'll end up with a0 plus a1 times x plus a2 times x squared plus all the way up to an minus 1 x to the n minus 1, and then you will take the coset that contains that polynomial. Okay, and do understand how this has changed, these additions and these multiplications. Okay, so if I do my usual highlighting in, this addition, this multiplication, this addition, this multiplication, this squaring here, this addition, this multiplication, this raising to the power of n minus 1. This was all done in my now field extension, my new field capital K, whereas of course now these additions and multiplications here have gone back to being in the ring of polynomials over the field capital F, and then we take the coset that contains the answer here. Okay, so this big bar means take the coset that contains the answer. Okay, right. Now, look at this. AIs can vary over any element of the field here. You can get any polynomial you like in the ring of polynomials over the field capital F of degree less than n. So you can take the coset that contains any polynomial in the ring of polynomials over the field capital F of degree less than n, but we know that that's all the cosets. Okay, that this lists off all the cosets. You can truly get to any coset you like by taking a linear combination of these elements of the field extension K with coefficients from the field capital F. Okay, so this is all looking good. That's the spanning portion. Now let's make sure linear independence is true. So Li we want to prove now. Okay, so how do we prove linear independence? Well, we need to prove that there can exist no non-trivial linear combinations that give the zero element of your vector space. Okay, so what we're going to do is we're going to suppose that a non-trivial linear combination does exist, and we're going to prove that it leads to something that is utter nonsense. Okay, so we're going to assume that some linear combination here, and I'll write it out again because I've made a mess of this one. So we're going to assume some linear combination a0 plus a1 theta plus all the way up to an minus 1 theta to the n minus 1, some linear combination of my basis vectors for the field extension K, does actually give me 0, the 0 element in my field extension K, so really the coset that contains 0. But again, I'm going away from using the barred notation because this is the way people do it conventionally. Okay, they want to view K as a field in its own right. We don't want to continue permanently stressing the fact that it is constructed from a quotient ring, although of course you do have to occasionally go back to remembering that it is constructed from a quotient ring in this way. But I won't put a bar over that, although of course we know that really it's the coset that contains the additive identity from the original field that is the additive identity in my new field, capital K. Okay? Right, so we're going to suppose that some non-trivial linear combination does exist, so that means all of these are not equal to 0, basically. Okay, at least some of them are non-zero. That's what I mean by non-trivial linear combination. The trivial linear combination is when all of the coefficients just equal 0 from the field capital F. Okay, right, so what does that actually mean? Well, of course, the way that we work out what the answer to this is we take the representative, which we'll do in exactly the same way, and then take the coset that contains that. So this will equal exactly what I've got here, and I'm now saying that the coset that contains this polynomial has to be equal to the additive identity in the field capital K, i.e. the coset that contains 0. So this is the point where you do need to go back to putting the bar notation there. Okay, so we're going to work this out, and we're going to then get that this polynomial p of x, well, sorry, not p of x, this polynomial here has to be in the same coset as 0. Now, what is the coset that contains 0? Well, of course, that's just our ideal, the principal ideal generated by the polynomial p of x. Okay, so why is that rubbish then? Well, because this is effectively saying that this polynomial of degree less than n is equal to some multiple of p of x. Remember, all the things in the principal ideal generated by p of x are of this form. Okay, now we know that all polynomials in here, all multiples of p of x, are going to have degree greater than or equal to n, apart from that silly one, which is the 0 polynomial, which we know this isn't, because we know that all of these coefficients are not equal to 0, because this was supposed to be a non-trivial linear combination. Okay, so we've arrived at utter rubbish. We've got a polynomial of degree strictly less than n equaling a polynomial of degree greater than or equal to n. Okay, so again, we've arrived at utter rubbish. So indeed, this set of vectors for my field extension over the field capital F is indeed a set of basis vectors. So this is a basis. Excellent. Okay, right. So that means then that we can write all of the elements of our field extension capital K, and indeed we often will write all of the elements of our field extension capital K as linear combinations of these basis vectors. So we can characterize now all the elements of our field extension capital K like so: a0 plus a1 theta plus all the way up to an minus 1 theta to the n minus 1, where the ai's are from the field capital F. Okay, and of course, really, all of these additions and multiplications are in the field extension capital K, so really, these should be the cosets that contain these elements, but we know that those are utterly identified in that injective homomorphism way with the elements of the original field, so we're just going to go from having to put the bar to actually viewing those cosets as being represented by this. We're just basically changing the symbols, okay, but it's now representing the elements of the field as they are in the sub-portion of this field extension, in that image of that injective homomorphism that we had. Okay, so we truly now are viewing the field capital F as just a subfield of here. Okay, and these elements are in K. Okay, we've just dropped the bar notation. Okay, so that just takes a bit of getting used to. So these now is a nice list of all of the elements of our field extension capital K. So we have indeed characterized the elements of our field extension. In particular, what we can now do is make a comment about what the degree of our field extension K over our initial field capital F is going to be. Okay, well that's just the number of basis vectors that we have. How many do we have? Well, from theta up to theta to the n minus 1, we have n minus 1, but then remember 1 here. Okay, so overall we have n. So the degree of this field extension K over F is going to be n, the degree of that irreducible polynomial that we wanted to add in a root to. Okay, so that's a really important fact, that when you construct a field extension in this way, by taking the ring of polynomials over a field and quotienting out by some irreducible polynomial, okay, you end up with a field extension that has degree n, okay, over the initial field, capital F. Okay, right. So we'll have a break here. We have now characterized the elements of our field extension. In the next video, what we'll do is explore this field extension in even more detail. We've characterized the elements now. Let's explore addition and multiplication in our field extension in the next video.